Something large, an extraterrestrial planet, has just been seen by James Webb. Furthermore, some people genuinely think that there may be a resident there. There is more to this planet than just another rock in space. Here's the crazy part: it's exhibiting odd symptoms, peculiar heat, strange chemicals, and other things that cause experts to pause and wonder, could this actually be alive? As of yet, nobody is actually discussing it. We may be the first to reveal this information. Stay tuned as we go further into James Webb's recent discovery and why it might be the first concrete indication that we are not alone in the cosmos. An impending milestone. The James Webb Space Telescope made history on June 25, 2025. The newly discovered exoplanet, now known as TWWA-7b, was directly photographed by it. This planet was no ordinary one. It was not a follow-up to previous discoveries, but the first time Webb has independently spotted a planet. More than 98% of the over 6,000 exoplanets that are known to exist have been discovered indirectly, such as by transits or wobbling stars. By providing visual confirmation in outer space, Webb's accomplishment smashed that stereotype. In the constellation Antlia, TWWA-7b circles a very young red dwarf star that is only 110 light-years away. That star, TWWA-7, is a cosmic newborn, only 6 million years old. A faint dusty disk, the remains of a planetary nursery, envelopes it. Webb saw the new planet in an opening in one of those rings. Clear, dim, and cold. TWWA-7b is the lightest exoplanet ever directly seen, with a mass comparable to that of Saturn. Only enormous gas giants that are at least 10 times more massive have been seen in direct photographs before. The game is altered by this. Webb may soon be able to identify smaller, maybe rocky planets if he can find anything this small and cold. The discovery was made possible by a unique coronagraph that was included into Webb's mid-infrared instrument. By obstructing the host star's dazzling light, it produces a sort of man-made eclipse that makes it possible for the telescope to see neighboring dim objects. The picture demonstrates that the engineering was done perfectly. The main astronomer, Dr. Marie Range, described the image as a quiet but significant moment, a glimpse of a planet in its infancy, observing a world in the midst of space, just beginning to take shape. This was more than a photograph. It was evidence that the Webb is now spearheading the search for new exoplanets and a snapshot of a planetary birth. TWWA-7 is an example of a stellar nursery in operation inside the stellar nursery. 3 separate rings of gas and dust, remnants of the formation of stars and planets, encircle this red dwarf, which is only 6 million years old. These rings serve as the fundamental units of solar systems, and TWWA-7b is sculpting its orbit and the environment it was born in. Webb has a distinct point of view. It provides a face-on view of the rings by looking at the system from above. This is not common. The majority of systems are skewed, making the entire structure invisible. In this instance, however, the layers of the disk are exposed, much like when you watch a clockwork mechanism gradually come into order. It is noteworthy that TWWA-7b was found right in the gap of the ring. Scientists have long hypothesized that planets are responsible for carving these holes in protoplanetary disks. They have the evidence now. As it expands, this planet actively clears its orbit and shapes its surroundings. The distance is even more interesting. The distance between TWWA-7b and its star is roughly 50 astronomical units, which is equivalent to Pluto's distance from our Sun. This goes against what we expected. Not every planet forms in close proximity. Some, like this one, are born far out, indicating that planetary systems can have more varied design than we previously thought. Its atmosphere will be the main subject of future online observations. Water vapor and carbon monoxide are chemical fingerprints that instruments may detect and may provide information about the weather and the development of this newborn world. Knowing it could help us understand how gas giants form and what circumstances might eventually make them friendly or unfriendly. Why is the game altered by this discovery? There is more to this discovery than only discovering a new planet. It changes the limits of what is feasible. It first demonstrates that Webb's image technology functions as intended. It's a huge accomplishment to use mid-infrared light to find a Saturnized planet 110 light-years distant. It demonstrates that, in addition to enormous hot Jupiters, direct imaging may now detect smaller and colder planets. Secondly, this provides concrete proof that a planet formed within its birth disk. We're not merely speculating, we are witnessing it. For planetary formation models, that is a game share. It provides a unique glimpse into the gradual formation of vast worlds from gas and dust. A new era in exoplanet discovery is made possible by the ability to image smaller, fainter planets. Up until now, only massive planets that were distant from their sun could be imaged directly. We're getting closer to picturing tiny, possibly inhabited worlds thanks to Webb's discovery. It sets the stage for the next generation of telescopes, such as the Habitable Worlds Observatory that NASA plans to build. Characterization, examining atmospheres, seasons, and maybe biosignatures, is the aim in addition to detection. The initial phase in that process is TWWA-7b. Lastly, it serves as a powerful reminder of our purpose. Stargazing is not all that humanity does. We are seeing the birth of planets. We are seeing our cosmic cousins come to life. This picture perfectly captures the point at when we ceased speculating and began to see. The atmosphere of the objective. The AR coronagraph from Webb does more than just take pictures. It collects fingerprints of chemicals. Scientists targeted spectrometers at TWWA-7b to examine its atmosphere when they saw it. Molecular absorption lines, which are discrete dips in light that signify certain chemicals, can be seen in infrared spectra. The objective for TWWA-7b is to identify substances that provide clues to the activities taking place in this infant environment, such as carbon monoxide, methane, or water vapor. Although there are currently no published direct data for the atmospheric composition of TWWA-7b, Webb's experience with other exoplanets provides hints. Consider K28b, where JWST found carbon dioxide, methane, and maybe dimethyl sulfide, indicating biological activity in its habitable zone world. At atmospheric characterization, WASP-80b and WASP-39b also detected carbon monoxide, methane, and water vapor exhibiting Webb strength. Astronomers anticipate that TWWA-7b's mid-infrared observations will emphasize chemicals associated with primordial atmospheres based on these examples. Why is it important? Finding these molecules provides insight on the formation and evolution of the planet. Water and CO trace structure for gas giants. CO and methane indicate atmospheric mixing and temperature. The presence of complex organics may indicate unexpected chemistry, but probably not life. Finally, the atmospheric fingerprint of TWWA-7b will be used to evaluate ideas of planet formation and whether similar characteristics are present in infantile Saturn mass worlds. Temperature is important to scientists as well. Thermal profiles can be seen in emission spectra. At some wavelengths, hotter atmospheric layers light brighter. By directly measuring thermal emissions, Webb's mid-infrared eyes are able to map hot and cold spots. Finding trends such as an unexpectedly warmer atmosphere could point to accretion energy or tidal heating, which are indicators of the planet's underlying structure. This step demonstrates that we are no longer merely visualizing planets in the larger movie tale. We are investigating their composition and operation. As a cosmic chemist for TWWA-7b, Webb isolates signatures, measures temperatures, and displays the vital signals of a nascent planet. Translated for an audience, it makes us feel as though we are hearing the planet's voice rather than merely seeing its outline. Disk dynamics, carving the cosmic nursery. The protoplanetary disk of TWWA-7 is a work of art. Unseen forces created 3 concentric rings. These rings were discovered prior to Webb by ground telescopes such as VLT/SP. However, the artist's brushstrokes were filled in by Webb's direct image. Infrared microns provide life to the discus structure. Gaps become visible, dust granules sparkle, and the position of a planet becomes obvious. Planetary carving is suggested by these disk features. Visible gaps are created as a developing TWWA-7b clears its orbit by sweeping gas and dust. Geometric certainty is provided via Webb's imaging. The planet is precisely in the gap of the middle ring. Important proof that it's not a haphazard dust cloud or far-off backdrop object. Planet-disk interactions are a fundamental scientific concept that is touched upon here. Young planets' mass and orbit have an impact on the shape of the disk. The disk then influences the growth and migration of planets. Webb aids in determining whether TWWA-7b, which is situated about 50 astronomical units out, is cutting quickly or slowly, influencing hypotheses regarding the development of Saturnian mass planets distant from their sun, a process close to star proximity that challenges conventional core accretion models. A unique flat-on view is made possible by the disk's pole-eon orientation facing us directly. The entire orbital configuration, distance, and planet disk setup are revealed by the Webb instead of the edge on rings. Clarity is added by this. Structure is not veiled or projected. It is plainly visible to us. Narratively speaking, this is cosmic building in motion, molded by unseen and visual storytelling. In this segment, viewers are immersed in planetary feedback loops, the way disks react to giants that emerge, and how those planets shape their environment. Additionally, it establishes comparisons with other systems, such as HLTA and PDS-70, which have identified disk gaps. TWWA-7b, however, is unique, subtler, younger, and lighter. Webb demonstrates that we are moving from static images to developing sketches of planetary birth, ushering in an era of sophisticated disk studies, an image that changes everything. With TWWA-7b, Webb's success isn't a singular accomplishment. It's seismic. By confirming that Mir's coronagraph can image Saturn-mass worlds, it surpasses previous Jupiter-class restrictions and opens the door to next-generation exoplanet science, photographing ice giants, lower-mass gas giants, and, with luck, super-Earths or even Earth-like objects. Imagine it as a transition from headshot to full bodies. We no longer make educated guesses based on transits, radial velocity, shadows, or wobbles. They are visible to us. Webb is more than simply a light sensor. It is a precise planet hunter, the companions that are hidden behind the star blocker. This alters our perception of exoplanets. TWWA, a proof of concept, is represented by a 7b. Massive planets may conceal a large number of newborn disks. They can be found on the Webb. This increased the number of known planets and provided statistical evidence for formation hypotheses by enabling the study of dozens of previously unobservable targets. It also establishes future expectations. Limits will be pushed further by missions like LUVOIR and the Habitable Worlds Observatory. Earth-mass planets in habitable zones are directly imaged. The stepping stone is Webb's Saturn mass milestone. We are seeing the first photos of a planet's birth that were previously only seen in science fiction. Additionally, this time highlights scientific and international collaboration. Candidates are outlined by ground telescopes. Webb characterizes and validates them. Planetary systems can be further explored with the help of the forthcoming Roman telescope and Hubble ALMA. TWWA-7b serves as the starting point for multi-wavelength, multi-platform exploration, much as planets in observatories obtaining their passport stamps. This marks the change from the discovery montage to the future roadmap in terms of filmmaking. The path shifts from discovering things to comprehending them planet by planet at this point. This serves as the narrative bridge to the following scene after disk structuring and atmosphere probing. What comes next if we can photograph this planet? What will Webb target next? When will Earth-like worlds appear? It prepares the listener for cosmic aspiration and thrill. A coal monster in the making, TWWA-7b. Young stars that are only 6 million years old, such as TWWA-7, provide glimpses into the formation of planets. Using his infrared vision, Webb discovered TWWA-7b, a frigid Saturn-mass planet, orbiting 50 Australian dollars away, nearly twice as far from our Sun as Neptune. Breaking through boundaries and demonstrating Webb's coronagraphic power, this world is the lightest ever directly seen, with a mass approximately 100 times that of Earth. It forms a clear gap as it floats in a three-ring debris disk, which is a well-known indication of planetary formation. According to simulations, its gravitational pull shapes the borders of the inner ring, resulting in the distinctive emptiness. Webb was able to scan this faint, chilly world in the thermal infrared by using a device called a coronagraph, which blocks out starlight and lifts the curtain on planets like Saturn, which is even colder at about 320 Kelvin. It is revolutionary to find planets with such low temperatures. Only the absorbed starlight from super-Jupiter was detectable by direct imaging in the past. A nascent, self-luminous planet is visible on the Webb here. However, this is not just a photo. It's a window. Scientists started spectroscopic follow-ups right away to look for atmospheric and chemical signs of CO, water, or methane dashes. We can investigate formation physics without being hampered by star heat thanks to its far-off, expansive orbit. Even Earth-class planets may soon be observable at these scales. According to models, our knowledge of how disks transform into planets is expanded by the discovery. TWWA-7 challenges prior theories that favor planets close in or of Jupiter-class size by demonstrating that Saturn-mass giants can develop rapidly and far from their star. This suggests that planetary systems are more diverse. Some might be much more like our own than originally believed. In the future, orbital motion through ring edges over years may be revealed by prolonged observation. Spectra can identify thermal evolution or atmospheric properties. Webb's next goal: look for worlds with comparable low masses. Mini-Neptunes, perhaps, planets in mid-formation, unset clouds, and moving dust. Rings could all be visible in the future. TWWA-7b is currently a vaporing baby that has just taken its first breath. Why does this alter the exoplanet astronomy landscape? The finding of TWWA-7b is more than just a piece of information. It marks the beginning of a new era in the investigation of extrasolar worlds. It first gives subJupiter mass direct imaging legitimacy. The discovery of a 100 planet makes it possible to target near-Earth mass objects that were previously thought to be unattainable. Future telescopes searching for Earth-like candidates in habitable zones will have a lower bar as a result. Secondly, it makes it possible to observe planet formation in IC2. Rather than using star dimming to infer planet features, we observe the planet forming its debris ring, or cradle. This direct confirmation links theories of planet-disk contact to empirical data. It also changes the way we think about system architecture. A large number of indirectly discovered exoplanets were near their stars. We can now observe that giants with broad orbits are common. According to Webb's discovery, planetary systems frequently contain distant giants that may have a significant impact on the creation of smaller inner worlds. Fourth, it demonstrates the convergence of software and hardware. While the Webb simple sensor picked up the dim thermal glow, the coronagraph blocked far too much light. The fact that it was a planet and not a dust blob was verified by coordinated simulations. This multi-phase validation serves as a blueprint for upcoming findings. It revitalizes the mission blueprint for the future generation. The Webb's use of direct imagery to search for Earth-class worlds will be emulated by projects like as NASA's Habitable Worlds Observatory. TWWA-7b demonstrates that accusations of technological immaturity are out of date. The scientific and public response has been ecstatic. Prominent publications, expert quotes, and prompt follow-up suggestions. Dr. and Marie Range refers to it as seeing a baby planet. Other astronomers concur. Webb creates a new orbital distance and mass window. A rare club is joined by TWWA-7b. Consider the difficulty of photographing a planet light-years distant to get a sense of why TWWA-7b is so significant. Up until now, The majority of direct photographs have shown blazing stars illuminating massive hot planets that are much larger than Jupiter. However, TWWA-7b deviates from that trend. Tucked away in a dusty disk surrounding a young star, it is relatively modest, roughly the size of Saturn, and it's the difference that matters most. The majority of the planets that we have captured were formed around large, brilliant stars that are clearly visible. TWWA-7b is substantially fainter and orbits a smaller star, a juvenile red dwarf. Its image capture demonstrates how our technology is able to detect more subdued, silent places. This is not a dazzling giant, but rather the birth of a planet similar to those in our own solar system. Gaps and dusty disks were long thought to indicate that a planet was clearing its orbit. The dust rings and gaps we have previously observed are those footprints. The planet itself now silently stands in that gap, proving our suspicions due to Webb. There is more to those dusty formations than just patterns. They are the outcome of planets influencing their environment. Discovering TWWA-7b is not a one-time event. It's an example from a textbook. Find a gap, snap a photo, and find a planet. In our cosmic toolkit, that is a potent new tool. It also paves the way for further discoveries. Across the cosmos, in dusty cradles, are worlds that are similar to our own. Where are we going next? There is more to TWWA-7b than meets the eye. This marks the beginning of a new era in planetary science. The next 10 years will see the introduction of far more sophisticated telescopes than the Webb, designed to directly see planets orbiting other stars, exactly what the Webb just demonstrated was possible. Consider NASA's planned observatory for inhabited worlds. Telescopes will be able to see its planets more clearly because to its improved coronagraphs, which are pieces that block starlight, and maybe a star shade, which is a huge flower-shaped screen launched into space to obscure a star's glare. The objective is to take pictures of planets that resemble Earth and look for life. TWWA-7b is ultimately just the beginning. There are more young stars with hidden planets and disks with gaps. We learned how to see them from Webb. It is now our responsibility to continue searching and to hope for the next discovery. Click the subscribe button if you share our curiosity for space and the unknown. We would love to have you join us on this adventure, as there is so much more to discover.